In algebra and pre-calculus classes, the method used for solving systems of linear equations is kind of intuitive, right? It's based on, you kind of look at the system and you say to yourself things like, well, that term doesn't have a coefficient, so if I start there, I can easily use it to eliminate all the other instances of that variable. Well, in this next series of lectures, we're going to develop something called a row reduction algorithm that we can use to analyze any system of equations with the goal of finding its solution set in a way that's much more analytic, much more procedural. So the first step in doing that is going to be to define some terms. The first definition here is simple enough. A leading entry is just the leftmost non-zero value in a non-zero row. A non-zero row being one that isn't all zeros. Now, the definition of echelon form is more complicated, but I think it'll be clearer if we look at some examples. So check out this matrix here. This one is not in row echelon form since it doesn't satisfy property 2. The leading entry in row 3, that's this 1, is to the left of the leading entry in row 2, that's this 3. Right? So property 2 isn't satisfied here. This matrix also isn't in echelon form since it doesn't meet property 3. In this case, this 1 is the leading entry in row 2, but it has a non-zero value somewhere below it. Okay, this matrix, on the other hand, is in echelon form. There are no rows of all zeros, so item 1 is satisfied. Each leading entry is to the right of the previous one, and all the entries below each leading value are zeros. Now, what I really want you to notice here is the sort of reverse staircase pattern that those leading entries form. Visually, this is what I always look for as a quick way to determine whether or not a matrix is in this form. So the reduced echelon form, or reduced row echelon form, it has these three properties here. The first one, not surprisingly, is that the matrix is in echelon form. In addition to that, the leading entry in each non-zero row has to be 1, and each leading one is the only non-zero entry in its column. Okay, so these two matrices here, just let you know right up front, they are not in this reduced echelon form. The problem with the first one is that it has a leading entry that isn't 1. Right, this 2 is the leading entry in the first row. Obviously, it's not equal to 1, so property 2 isn't satisfied. Now, looking at this second matrix, this one doesn't satisfy property 3. This 4, for example, is a non-zero entry in column 2, and the leading entry in row 2, column 2, is that 1, so it can't have a non-zero entry above it. All right, this matrix, on the other hand, is in row echelon form. And again, if you're looking for just quick visual cues, you notice how it's got that staircase of 1s, right, that diagonal of 1s, with zeros up and down. And all of the non-zero values are to the right of the columns with the leading values in them. Now, just kind of looking ahead a little bit, right? If I were to take this matrix here and think of it as an augmented matrix and rewrite it back as a system of equations, it would look like this. Hopefully, you see why this is a desirable thing, right? This is essentially the solution to the system of equations, right? Each variable has a single numeric value. So this reduced echelon form, this is going to be kind of a key player a few lectures down the road when we start trying to really develop our solution algorithm. Now, mathematicians, we tend to get a little obsessive over trying to figure out whether or not something is unique. Right? So looking at our new matrix forms, the echelon form is not unique, since a matrix can have multiple echelon forms that are row equivalent. These two matrices, for example, are row equivalent since we can get the second one by dividing every term of the first one by 2, and they are both in that echelon form. The reduced echelon form, however, is unique, right? That would be the right hand matrix here. You'll see this also reflected, in the way we talk about these terms. We'll often refer to an echelon form of a matrix versus the reduced echelon form.